Welcome to this e-lecture on power, precision and bias. This will have a little bit of revision about precision and bias and put this into the context of power and sample size estimations to get you ready for this week. So let's start with bias. You should be familiar with this term by now, but just to go over this quickly. Bias results from systematic errors in the research methodology. You can see from the two diagrams below, the one on the left has scattered estimates, with the truth being the bullseye. You can see that these are all scattered in one direction, meaning there is likely to be bias in the way that these have been estimated. Whereas the diagram on the right clearly shows that the estimates are scattered randomly around the true result, suggesting that there is not necessarily a bias in these estimates. However, they do lack precision. Common examples of bias are selection bias, to do with the recruitment of participants into the study, information bias, such as social desirability, recall, observer and misclassification bias, which are to do with the way information is collected and stored in your study, and intervention bias, to do with the way the intervention is delivered, such as issues in blinding and randomization, or the actual delivery itself, which has introduced a bias. One of the optional papers for reading this week goes into a lot more detail about these if you'd like a bit more revision. Next is precision. Precision is the repeatability of a measure and getting the same result time after time. That would give you very accurate very precise data. However, this is not always accurate. As you can see, again, the samples on the left are very precise because they're clustered closely together, but they're all skewed to the side of the true value. This suggests that the measurements are precise, but have some sort of bias in them. Whereas the diagram on the right demonstrates what you're aiming for, something that is precise and unbiased. This is summarized here in this diagram, along with the two most common ways to deal with increasing your precision and reducing your bias. Increasing precision is usually dealt with through increasing the sample size, whereas reducing bias is commonly dealt with through randomization. Although, as has been discussed previously, you should be thinking about all the different types of bias that could be introduced into your study throughout all stages of study design, whether you're doing a randomized study or not. So, let's look at a hypothetical situation where you have a null hypothesis of a population mean of 0 and an alternative or an intervention group where the true population effect is 3. And we want to do an experiment to see whether the population we're studying has a population mean of 0 or the alternative of 3. We conduct a study which gives us a sample estimate of beta. This is just below the value of 1. So, did our estimate come from the null hypothesis, the H0 group, with a population mean of 0, or the alternative, or the intervention group, with a population mean of 3? Now, the way that we would normally estimate whether something is significantly different from the null hypothesis is to draw 95% confidence intervals. However, to note, these confidence intervals do not always need to be set at a 5% significance level. You commonly see confidence intervals of 90% and 99% as well. Here you can see these are drawn as the lower bound and the upper bound of the confidence interval, with the estimate of beta sitting firmly in the middle of the distribution for the H0 situation. So based on this, do we think that beta is significantly different from 0 at the 5% significance level? In this answer, we would likely say no. However, what about the difference between beta and the alternative situation, with the true effect of 3? Is this significantly different from this population mean? In order to calculate this, we would need to know the power of our sample to decide whether we can confidently reject or accept the difference between beta and the true population value of 3. What this means is that a very unlikely situation is that less than 5% probability of a difference that is solely due to chance. In this case, we would reject our null hypothesis. This is essentially a p-value of less than 0.05, means that less than 5% of the time we would expect this value to be found by chance. In this case, we would say that our program has a statistically significant impact. However, this also means that 5% of the time, we will say that our program had an impact when in fact it didn't. This is what is known as a type 1 error, and this is what is measured through significance. So this is the problem where we say that something is statistically significant when in fact it isn't. You can adjust this and be more conservative in your estimates by changing the significance bounds that you use, such as having a p-value of less than 0.01 as indicating significant. However, in other situations, you might also want to increase that to say a p-value of less than 0.1. However, it is standard to use a p-value of 0.05 or a significance level of 5. But what about the other situation, where you say that something is not significant, even though in reality it is? This is known as a type 2 error, and this is measured through power. This is to put it into more scientific terms, instead of pictures of pregnant men and unpregnant women, where the true positive means that you have a significant impact and there's also a treatment effect. A true negative is where you do not find a significant impact and there is no treatment effect. A false positive, or the type 1 error, is where you reject the null hypothesis and say that there is a significant effect even though there is no treatment effect. With a significance level of 5%, you would expect this to happen 5% of the time. A false negative, however, is where there is a treatment effect, but you've not found a statistically significant result. This is a false negative or type 2 error and tends to happen when you're lacking power in your study. So what is power? Power is the probability of avoiding a type 2 error, and traditionally we'd aim to have 80% power in a study, although in some cases you'd want to have 90%. This depends on partly the research question you're asking, the budget and the resources that you have available, and whether something is critical and the clinical significance of what you're looking at. So, in that example before, the upper bound of the 95% confidence interval sits at that yellow line. The shaded part in the alternative situation, or the beta hypothesis, is the power for this. This shows an 80% power to see a significant difference. The reason this is important for sample size is because as you increase the sample size, you tend to get tighter distributions and less variability in your results. So you can see that those curves will become thinner, which means that you are more likely to see a difference if you have one, compared to a wider curve where you're more likely to have more overlap. You can see this if we plot out different sample sizes. So the shaded part in green is currently a 95% confidence interval. So this is the upper bound of the 5% significance with 1,000 participants. Then you can see if we increase this to 4,000 participants, that significance level is covering less of the curve for the alternative hypothesis than previously. And if you turn that into the power, you see that you have 64% power to detect a difference at a 5% significance level with 4,000 people. If you increase this to 9,000, you can see the overlap between the significance bound and the alternative hypothesis is getting larger. This means that you now have a 91% power to detect a difference at the 95% with a 95% confidence interval between the null and the alternative hypothesis. In the sessions this week, we'll be talking through how you calculate what sample size you need in order to detect statistically significant differences for different scenarios using proportions, means, and case control studies.